Hi. For our 4212 final project, we developed TetrisBot, which is an end-to-end robotic system that plays Tetris. The motivation behind developing TetrisBot is that we've seen that the combination of unrealistic game elements that require complicated simulation and fine-grained pick and place is pretty rarely explored. And we choose Tetris in order to explore this because it satisfies both of these criteria. Um, Things like row clearing and piece teleportation require like complex simulation, and at the same time, we need highly precise manipulation in order for pieces to be placed pretty right next to each other. And Tetris has the potential to impact a lot of robotic games and interactive simulators, such as things like Connect 4, chess, or Jenga. And as far as we're aware, this is the first Tetris playing robotic system that we've seen.
And so, as we've seen in this class, there's a wide range of projects being explored in the space of robotic manipulation. So we just wanted to highlight some that we felt also touched on some similar aspects as TetrisBot did. So as we mentioned, as we learned in class, we learned about the dishwasher loader robot, which we saw those aspects of object identification, graph determination, and trajectory optimization. In the shopping cart example, along with the localization, there was also this aspect of optimal piece placement, which is very important in Tetris. And finally, looking on more of the gameplay side, you have Jenga with that adversarial uncertain gameplay, which is a very important part of Tetris as well.
So here's a brief overview of the methodology of TetrisBot. We first construct and teleport a random piece, and then we detect said piece using a convolutional neural network. We pass in whatever our detection algorithm returns to the gameplay algorithm, which returns a rotation and a position. We transform that into board coordinates and then place that piece at the desired location, and then we update our board state if necessary. Going into a little bit more detail, in order to construct and teleport a new piece, we require a simulation loop, which is pretty crucial for this entire project. And that's because certain aspects of Tetris can't be simulated using things like the physics engine, which is what we've traditionally used in class so far. Things like being able to spawn a piece at a given location or replace every piece once we put it on the board with a series of unit cubes in the same location to make things like line clearing easier are things that we can't do without breaking out of the simulation. Once we have that randomly generated piece, we use a convolutional neural network to detect which piece we've teleported in. And we use a MobileNet CNN in order as like our base network, and we train a couple of layers on top of that to determine which of the 7 pieces we've randomly generated.
Once we figured out what piece we have, we can then use our gameplay algorithm, which will basically determine what the optimal position is to place that piece on the board. And that's using heuristics like the height of the board after any line clears after that placement, or like the actual placement on the board of that piece, like how low that piece can go. And these are heuristics that are used by players that are playing Tetris, and we felt that they would be effective at teaching the robot how to play Tetris effectively.
For the final two steps, we go a bit more into detail in the next two slides. So for picking and placing, we plan a trajectory for each piece. So what that does is it composes 4 key poses to construct this trajectory, which are the initial pose here, a grasp pose, an intermediate pose, and finally a drop pose. The grasp pose is fixed for all the pieces and is able to pick all of them up. And the drop pose incorporates information from the gameplay algorithm, which is the rotation of the piece, the desired row and column to drop it in. After dropping the piece, we update the board state. So what that involves is populating cubes in the location of that piece. And also if any rows are full, we clear that row. And in these images, we see the before and after of a row clear. Here's a demo of our TetrisBot in action. We can see that we have a successful end-to-end simulation of Tetris play. There's very precise grasping and placing of each block, and each one lands where desired on the board. We can see that all the pieces are being identified correctly and placed correctly, and the gameplay is pretty reasonable.
Yeah. And so, as we were working on this project, there were a couple of extensions that we were thinking about. So, obviously, we want to make a more robust, more optimal gameplay algorithm using elements such as reinforcement learning. Hopefully, we thought it would be interesting to make a multiplayer version of Tetris that has multiple EWAs playing against each other on the same board. And also, we'd like to make a more true-to-life board that has either a vertical or slanted board so that we can utilize that aspect of gravity and, simulate actual gameplay with increasing gravity, perhaps. Thank you.